Dobar dan po treći puta u ovom našem tjednu SCIA. Hvala vam puno što ste odvojili malo vremena da vidite i novitete i ono što rade vaši kolege konstrukteri. Danas mi je čast predstaviti našeg dragog prijatelja, BIM menadžera, čovjeka s kojim sam se i družio osobno dosta puta na raznim Alplan i SCIA eventima po cijelom svijetu. To je Ciprian Popa, BIM menadžer, čovjek koji radi magiju i sa SCIA-om i sa Alplanom. Osim toga, on je i osnivač tvrtke Structural Glass Design. Ni više ni manje napravio je i novi modul za samu SCIA-u. Dakle, integrirani software za proračun staklenih konstrukcija direktno u SCIA. Dakle, SCIA je bogatija za još jedan dodatni modul koji se tiče upravo proračuna stakla, a napravio ga je Ciprian Popa. Ciprian, da ne duljim, izvoli, hvala ti što si s nama. Ugodan dan.
Okay, so welcome everybody to today's presentation regarding light gauge steel structure challenges and the BIM solution. I prepared this presentation with help from Professor Zorano, but now he couldn't be present at this very moment. He has some urgency things to solve. However, I have received some very nice input, some materials, and I'll be happy to present them on his behalf. So let's go forward. So what I'd like to present today is what is this light gauge framing system? Maybe it's not something very familiar for everybody, but it's something that is quite a hot topic on the market. This is why I chose to present about this. So it's about a steel structure which is made from light cold form profile. So you see here from the distance, and if you cover the structure, it looks just like your typical house. But imagine that the profiles you see here are 1 millimeter thick. So they are just in a proper shape in which you get economy. So imagine you only have to take sheets of steel of 1 millimeter, you fold them in different complex shapes, complex and smart shapes, and you can obtain any kind of structure with advantages and disadvantages. Actually, this is also a topic here. I'm not selling you these profiles or this structure. I'm just exploring and want to share the knowledge and my experience when designing this kind of structures. But the pressure is very high from beneficiaries. So it's a hot topic because, as you might know, prices exploded recently due to the lack of stocks as a result of the pandemic situation. And for steel, for instance, the price is doubled. So imagine the price for material doubled, the materials are 70–80% of the cost of any construction. It's impacting a lot, and most people are looking to do some economy. So light steel is kind of a smart steel. So it's just same material as steel, but it's positioned in a smart way to gain some economy of material. And I will present some case studies and what are the design challenges when you want to calculate such a structure, and also some experimental validation from Technical University of Civil Engineering from Iași. So as you might know, or you who know now, the university has one of the biggest seismic testing platforms in Europe. It is very impressive. And I actually got some footage from Professor Serrano where they tested in reality such a structure and draw some conclusions, and we will comment them together. So I hope it will be an interesting presentation for you. And towards the end, we will leave time for questions and answers. So I will briefly go. I cannot teach you steel and light steel here, but I just want to point out some ideas. So you see here another example. So light gauge framing system is a construction technology using cold form steel profile as a construction material. So cold form is when you take a sheet of steel and you bend it, compared to laminated steel, where hot steel is obtained from a lamination process. So you get some specific profiles that are produced in a heated environment. So from the beginning, there's a difference between the production of the steel to obtain the full technological process, and obtaining the profiles is quite different. Now, light steel can serve both as primary and secondary structures. So it can also have the role of a secondary structure, which is like you'll see in partition walls. So if you know brands like Regips, like Knauf, all those partition walls have a steel structure within them. Those are called secondary structures. So it's a structure of a non-structural element, because the element itself is made of some plaster boards, and in between they need a steel. Now the idea is that you can, with this concept, you can build both the structure and the partitioning with the same material. And they say that it can substitute traditional materials like masonry, like timber, and so on. And you can create everything from external walls, floors, everything with this kind of technology. And also it's using better quality steel usually. So producers like Tata Steel from India are producing this high strength zirconium. So this is one of their products. And it has quite a big resistance, and also it's good for environmental corrosion. So you see its yielding strength is also quite high, is 550 megapascals compared to steel, typical steel, which is around 250 up to 355. So it's also a higher quality steel involved in producing this kind of profiles, which again, they are just a few millimeters thick. And now this picture has nothing to do with our presentation, but I'd like just to briefly discuss about some differences between heavy steel or structural steel. There's not a name in the industry as heavy steel, but it's just structural steel, but the other is called light steel. So both produce, those are the muscles of the building, meaning that they provide structure and stability to the building. So what is structural steel? So steel in construction is renowned for its strength and versatility, and with different steels available on construction projects, it's important to know what are its main benefits. So steel is used for large building projects with construction such as multi-story building, bridges, industrial plants. And the main reason is it has a lot of advantages. It's strong. So structural steel is hot rolled, and once hardened, it becomes very strong. For comparison, 1-inch circular bar that is firmly attached to supports can hold 20 tons. Time cost efficiency. So structural steel is easily produced and put together. It is created off-site and assembled on-site. This makes structural steel time effective as it speeds up the construction process. In the long run, it will also save cost on time. Time is money in construction, as everybody knows. So with steel, you actually have a cleaner site, and you don't waste too much time on the site. So the production of steel starts in the factory. You have some profiles. You create the assemblies in the factories. They are sent to the site, and on the site, after you build the foundations, you start adding the steel structure, and you just connect both the assemblies and weld if there are any weld connections there. It is relatively cheap as other building material. This is arguably debatable, especially that the price for steel has doubled recently, and is durable because it can withstand external pressures, earthquake, thunderstorms, but also still has its own disadvantages. So disadvantages are regarding corrosion. Steel is an alloy of iron, and this makes it susceptible to rusting or corrosion, and can be solved using anti-corrosion applications. Now, the problem is that these applications are not for the lifespan of the building, so you need to maintain this structure. So therefore, you have some high maintenance costs. Despite being cheap to make, steel in construction comes with high maintenance costs. It has to be painted to make it corrosion resistant. The anti-corrosion costs, also high cost that comes along with fireproofing. So steel is also vulnerable to fire, and you need to have some fire treatment on the steel. And treating it against fire is also, you have to do it every 5 years, and includes adding either plasterboards or special paints. So it's a process very delicate, because imagine you make a structure, you cover it to look nice, but then after 5 years, you need to take all the covers there, retreat the steel and apply it again, which is a lot, it's generating costs. Now with light gauge steel is cold formed. So the other was hot rolled. That was one difference. And they are made of thin sheets that are shaped in either C or Z shapes. You'll see them in a few moments, but you know the letter C and Z, it's not a problem. So this kind of frames are produced and fabricated from steel quality steel coils, and they are shaped at ambient temperature by rolling form machines. So they provide a lot of advantages. So they are time effective, they can result in faster building, and the high strength in safer, less maintenance, lightweight. So again, the steel is very strong, it's 550 megapascals, and it resides in lighter foundations, and also the structure being not that heavy. The earthquake does not cause any big issues. So if it's light structure, it has a small mass, and earthquake just brings some accelerations. You multiply the small mass with the acceleration, then obviously you get smaller seismic forces for this kind of structure. The quality is higher because it's a very special steel used. And also it's recyclable and allows expansion and relocation. So if you want to move the house, you can just disassemble it because it's all on bolts, and you move it everywhere else. If you have a bad terrain, or you start from a zone and then you have a better terrain somewhere else, you just unfold the house, unscrew the bolts, and you can move it. Or you can change the floors. You can start with something small, but then children appear and you can add another floor to it. Not that many, 1-2 floors. It's not susceptible to that. But also in plan, you can make some extensions because it's a very flexible system. Okay. And lower construction costs because they are very strong and lightweight. So less material, less money. This is what most investors look at. How many kilograms of steel does this structure have? And as I discussed with the engineers who are attending the SCIA course, it's all about the money when it comes to investors. So choosing an engineer, it's not about the money he asks, but it's about the money he saves. So I did an experiment. I asked last time in SCIA at the course, how much money would you charge for the building we were doing at the course? And we got different prices. And I told them that prices are actually not that relevant compared to the money you can save with a good engineering design. And now, as we're not here to sell this steel, we need to talk also about some disadvantages, which are quite a few. I just noted some of them. So they can lose properties in time, like structural steel, and in case of fire, it's horrible. I mean, if fire reduces a lot, it can reduce to 10% the actual resistance of the structure in just a few minutes. So usually the solution with steel is to provide plaster boards or other materials that fight with fire. So fire first consumes those materials that burn slowly, and then when it gets to steel, it really reduces very fast the structure. So if you design the structure to resist steel, it should be 10 times bigger. Usually you have some solutions to solve these issues. Supporting structure, so this steel frame construction rarely work on their own. They usually require drywall, sheathing, insulation, and some supplementary wooden components to bring a building together. So you will not live in that skeleton. Obviously, you need some partition elements, some panels to close it, to feel the intimacy you have from a wall. So it's an additional cost. You don't, if you just evaluate the skeleton when you want to build your own building, it's just not enough. So in opinion of some construction businesses, this longer construction time is an argument against steel structures, although usually the time saving, any adjustment need to be done on the site. Now, let me just show you a bit how this kind of structures work. So this is a model of a house. Actually, this was an offer request from a manufacturer of skull form profile. So this is a one story and a livable roof. There are special dedicated software who produce this kind of profiles, but also with this BIM environment, and this I used BIM in the name of the presentation because you can model it in 3D in a software, and then the IFC calculate it in other software, and then do the connections in another software, and so on. So there's no such thing as a software that can do anything, but it's very important to be able to communicate, of course, with people, but also software with software is another thing that BIM is relying on. So if we cover this house, especially I did not cover it because it would look like just a typical house. You see here the profiles. Again, these are, I'm not sure if it's 1 millimeter or 1.5 millimeter, but imagine it's yeah, it's 1.2 millimeters. If I switch this to millimeters and get here, 1.2 millimeters. So this is the thickness. Imagine you just take a sheet of 1 millimeter is very, very small. If you just look at the ruler, how much small it is, you'll understand. So it's very, very small. It's in this shape. So from the distance, they look like pipes, but actually they're not pipes. They are profiles that look something like C. It's a C shape, but it has also some small fins. So I can just generate a section for you to understand better what I'm referring. I mean, it's not the letter C you learn from school. It's a construction C. So I generate just a section through this. So this is how profile looks like. So it's a C with some extra lips. So it's a very, very thin profile used. And the advantage is that you can have, we can vary these dimensions. So you can have different variations for these profiles. So you can change the height, the dimensions of the flanges, and so on. So it's 100 millimeter tall in this example. And this profile is placed in so many positions, a lot of bracings or frames or trusses. So you play around and you can model this kind of structures in 3D. The structure is very complicated, as you see here. So although it's easy to produce, it's just a sheet you fold and cold, so you don't even need in an oven or something. but it's very delicate and the design is very complicated. So just look at it, how many profiles are compared to some concrete walls or some concrete masonry. It's a lot of work to model this, and also you need to connect everything. And it's also very challenging to calculate all the bars and to do the assembly plan. So imagine that for building this, maybe you don't even need the crane. You can just be a husband and wife carrying these profiles. They are very light, just a few kilograms. But the idea is that the plans are very complicated. You need fabrication plans for each bar. And also, after you fabricate, each bar will have a barcode to identify its position, its unique identity. And in the plan, you need to indicate where these bars need to be placed. So it will be challenging. It's really like a Lego. And it's actually a Lego you can do even without crane. But you imagine that you first need to look for the piece when you build this Lego, and then you need to see where you need to place, and then you continue like that. So it's quite challenging to design it. It's a lot of effort to do it. And for site, indeed, you don't need that many people and you don't need that special equipment. So that can be an advantage because it's very easy to transport this kind of profiles. They're very light and they can fit in normal vehicles. Okay, but designing itself is quite complicated. Luckily, with this BIM technology, we are relying on IFC. So industry foundation class helps us communicate with most certified, with most software. Those who are certified can have guarantee that the transfer is okay. SCIA and Allplan, as discussed previously, are both IFC certified. So this is how this is the main part of the structure. It's not finalized, but mainly you'll see that these are the different profiles used here. And these are the connections, and it's quite a lot of work because even if you use IFC to import, actually the project was done in Vertex, exported into IFC, and then brought it here into SCIA Engineer. It's quite challenging because even if you receive the structure from architecture or from special tailored products for this kind of structure, it's still challenging because when you calculate and do a special 3D analysis, all these bars need to be linked. So all these bars need to connect in nodes. Otherwise, if you don't connect in nodes, you don't have static schema and the structure will not be able to calculate. So this is not a finalized project, but I can show you some other projects. Let me just open some other application of this kind of structure. Just a moment. So this is a parametric study for halls where they want just warehouses where nobody lives. And in case of fire, that's it. It's the merchandise that it's lost due to this fire vulnerability. So to protect this from fire, it costs a lot. This can be one idea. You see here, this is one idea of building trusses. So although from distance it looks like very strong structure, again, the profiles are just a few millimeters thick. So if you double click here and have a look, these are from database, but the thicknesses are very, very thin. It's 1 millimeter or something, but the details are quite complex. So these are 2 bars, there is a gusset in between, and most bars are made of pairs. So they are pair of those coliform profiles. The span, in this direction, the span is not that big, it's 4.2 meters. And this is how it looks. So also the purlins on top are made of coliform steel. Actually, coliform steel is highly used in industrial applications for purlins. So even for structural steel, the purlins are often made of light steel of cold form profiles. Let me show you some other solution for this kind of structures. So again, this from the distance looks like your typical hole, but if you zoom in a bit, you'll see that it's very complicated actually. So it's these C's that are quite complex. They're thin, but I will show you how complex a detail looks like if you want to produce it or calculate it. So from the distance, it looks like it's a profile of an eye profile or a pipe, but actually it's just very thin elements welded. So just have a look here. In order to get enough capacity for this column to bear snow, to bear wind, to bear everything, this is how the details look like. So this is a C, there's another bigger C on the flange and so on. So this is the required level to be able to assemble with elements that thin. And this is these are some trusses, and all the trusses are all the elements like diagonals, chords, and any element is made as a pair because in between there's a steel gusset to which it connects. Also, you cannot really weld this kind of profile. So if it's 1 millimeter, 2 millimeters, the thickness of the steel, imagine you cannot weld it. How thin can you make that weld? So you are required to make bolt connections. Bolt connections are friendly because everybody likes to tighten bolts and have flexibility, deliver assemblies, and just connect bolts on the side. Now, the problem is that you need a lot of bolts. So this profile, you've seen they are made from a very special, strong steel. And that steel, in order to be able to, that connection, in order to be able to transfer the capacity of one steel element to another, it requires a lot of bolts. And also you cannot work with that big bolts because you don't have place, you barely have place to position one bolt. Let's see if I have anything else interesting here to show. So this was another idea to try to avoid those trusses, to try to simplify a bit. Actually, this is also with trusses, but there are different variations trying to get the consumption. So this was like rush for gold, or we tried to find the philosophical stone. So the challenge was to obtain some consumptions like 10, 11 kilograms per square meter, which is very, very low. I mean, a typical hole has around 55, 65 kilograms per square meter, and this fabricator wanted 11. So we couldn't do it. We tried, we made all possible shapes, and we only got to about 30 kilograms per square meter for everything, but it's still okay. So it's almost a half you get from normal steel. So consumption-wise, yes, you have less material if you do cold form, but the complexity is so much higher for the design, for the montage part, and to connect everything. It's very, very challenging compared to having just some steel you buy from the shop and you connect. Very simple on site, and you don't have so many members required here. The span was also quite high, and also there's a big problem. Many of these cold form profiles come from countries which don't have snow, so they can be positioned very nice in desert. In desert, it's good because these are corrosion protected, but in desert you don't have snow, you just have wind. It can work. Also in UK, you don't have that much snow, or in many regions, like in Israel, we don't have snow. So in a region where we don't have this big load on the roof, it can go more economical than we obtain. But for Romania, we could not obtain this dream. It's cheaper, it's less material, but not really easy to manufacture and execute. Now, as I said, one of the biggest challenges for this, I think also I have another application to show you. It's a greenhouse. So this kind of profiles can also be used in greenhouses. So this is made on arches. This is a greenhouse structure. So mainly there are vegetables growing there, enjoying the sun, the heat, and so on. And this is how it looks. It's quite complicated to bend them. They are made of straight elements and connected via gussets. It's quite difficult, but this kind of structure, trust me, they exist in Romania, at least also in Europe. But in Romania, it's quite challenging when we think about the snow. Of course, it's very debatable. The problem in Romania is that the snow is overestimated and it's not aligned to the global warming. I mean, when was the last time we had problems with snow? Just think about it. And in Romania, you have very big values evaluated for snow and you're obliged to follow those rules. But just as a thought, if you look in city of Iași, where is the base of this event, the evaluated snow according to Romanian code is 250 kilograms per square meter. Now that's a lot, trust me, 250 kilograms on every square meter of the roof, it's a lot. Now, if you just take the car and drive 1 hour and get to Chișinău, there you have 50 kilograms. So it's snowing five times worse in Iași than in Chișinău, and it's under 100 kilometers in between these cities. Of course, different country, different politics, but again, it's kind of exaggerated, but you as designer should just follow the regulation. You cannot say that, global warming, the snow will never come again. You cannot say that. But the problem is that you are, as a structural engineer, you are brought some projects you get from outside, from Europe, and you need to adapt to Romania, and you cannot do it because of these regulations. So let me show you also some connections. So this was the previous project I showed, and you can design connection. Now, these are not connections I recommend, to be honest. We just made some checks of the connections. We don't like the way they are. It's not a project, we just made some evaluations. So this is, as I told you, this is a real project and for greenhouse, and there are different types of connections. So this kind of connection is very good. It's like for typical steel, and it's for typical steel. It has nothing to do with the light part. Now the problem is with the base connection. And let's have a look on how it behaves. So here is the concept. You have two L profiles at the base, and there are some bolts, and the profiles are welded in this base. So it looks like this, the connection. And also here on top, there's a continuity connection on the arches. So the model looks like, just a moment, make sure it needs some alignment. This is Idea Statica. It's an excellent software for connection design, and it collaborates with other software like SCIA Engineer. So it just needs some alignment to be done. The idea is that this profile was done as a pair profile. So it's a general edition, and there are the pairing has been modeled as a single element. And there can be some offset. I'm not sure in this why I did not insert it properly. Let me just adjust it now. I think it's just something like 200 here. And you have a weld marked here. The weld is actually for both elements, but this is a special situation. This is not a connection that I respect. I'll show you how this connection should be done, but it was just a challenge to be able to demonstrate that connection is not okay. So the purpose of any connection is to be able to transfer the load from one element to another. And another rule when designing connections is not to fail in the connection. So the connection always needs to be stronger than the element it's connecting. So that is one thing engineers know, and this is a principle when designing connection or joints in any kind of material or not. So we're not going to waste too much time here with this model. A continuity connection would be something like this. And also here are examples of how connections should actually work. So if you want to design cold-form connection, then here are some better examples than what I shown you previously. So that was an evaluation of current things that weren't okay. This can be an apex connection. I will not open the models, but I'll just briefly explain them. So you see there's a gusset and a lot of bolts. As I told you, this steel resists a lot. If I want to transfer the capacity of these two to these two, I need a lot of bolts because I cannot use big bolts. I need to use a truck of load of bolts. And bolts are very expensive. They are more expensive than the steel, normal steel. This is how a diagonal connection would look. This is a column-based. This connection was provided by CMA Construct Development. So they did this kind of analysis for steel construction. This is a beam column connection. So it's a gusset that connects the column with the beam. So these are kind of connections that can be accepted. But again, have a look of how many bolts you need to screw. And bolts, as again, are very, very expensive. So a kilogram of bolts is 10 times more expensive than a kilogram of steel. And it's a more complex joint for a truss. You see, these are the bars entering the truss. This is how they connect and how it looks. Okay, now let's get to the interesting part. So as I already explained, what are the challenges? I showed you that it is possible with proper software to calculate these kind of structures. But let's see what science has to do or physics has to say about this kind of structures. This is a model from experimental model. This is the testing seismic laboratory in Iași. And if you visit Iași, you can actually see this structure. It's not the nicest structure you'll see. So it looks like a cage, in my opinion. But of course, there might be customers who want just a few kilograms to build their house. Let me show you also in 3D how this house looks like to get a better understanding of it. So we'll just close the other models. So this is mainly the geometry of the house. Okay, you just enter and you exit from here. A lot of bracings, normally you will not see them because this should be covered in plaster. So you'll have windows where you don't have bracings and you cover them with plaster. So you just see a flat wall. You don't see the skeleton, but I'm showing the skeleton to analyze it from structural point of view. There's also some truss on top. And getting back, let's see how this behaves in reality. So let's just try. I hope it will have also the sound. You can also find this on YouTube. Actually, I'm going to share with you the link. Sorry, I opened the plan. So yeah, it opened 3 times. So I will share just for you to have to be sure you also hear the annoying sound that you get from these experiments. So it's on YouTube as well. So let's watch it together and comment the way it behaves. Professor Serrano is here filming with his phone in the movie. So let's have a look here. So you see that there's also 2 kilograms per square meter. It's the snow that you have on the roof, as I was talking about. It's heavy snow. And you'll see that the frequency is 1 hertz and acceleration is 0.6 G. It's a lot. It's more than the code demands, but there's no point in just, you always wanted experiments to see also how it fails. So don't imagine that this structure is vulnerable to seismic forces, because it's not. But it's fun to watch it move. So let's play. It's in slow motion now. You see here, we'll just watch this portion. You'll not see any plastic hinges, everything is elastic, but you will see buckling of the walls. So have a look here, you'll see how this element buckles before getting to yielding. So that's one specific, look here, this is buckling. So one specific aspect of coliform profile is that they buckle before they yield. So there's no plasticity appearing in this kind of profiles because it buckles before it consumes its capacity. So calculating such a profile is very demanding because you need to evaluate the effective thickness, the effective characteristics for bending and axial force. And as I said, this experiment is not 100% relevant because the covering, the cladding, even if it's just a sheet of wall that is covering both faces of that structure, that will help a lot it will help the general behavior. So mostly it will prevent buckling from happening, but it's not necessarily. I mean, it's just a thought. Now, what we learned from this experience, the structure was modeled in Axis VM, I believe, and this was the eigen frequencies, the expected, the deflection shape. It kind of looks with what it had there. And actually the scope of the experiment was to determine the real thickness of the elements, of the stiffness of the connection. So the connection used is a very simple connection. It's one bolt connection. You see, this is the bolt. This bolt is made of better steel than the profile. This is why it's more expensive, as I said. So you see here that under forces, under axial constraints, because it's obviously hinged structure, you see that the walls fail. The walls of the profiles fail. No wonder they're 1 millimeter thick. But you see how they deform. So it makes some plasticity around, and this is how it fails. And what you see here is a force displacement diagram. Up in here, it's linear, but then it curves because it starts to deflect under constant effort. And also because you see it's already plastifying, you get rotation and you get higher displacement. So the problem is with this kind of structure, it will fail in the connection. So it's not a safe structure because a safe structure usually moves the failure zone to columns and beams. Maybe there are also architects here and it might look not that nice to them, but you know that as engineering of the building, you have to decide where you want it to fail because you can never design a structure to bear all its possible forces. It can always come a tornado, an explosion, or a bigger earthquake than you imagine. But the idea is that the way it fails should be safe and reduce any casualties and damages. So this is why it's a big pain here, because we can accept all the bars to buckle, no problem. But if the connection fails, then the whole story fails and game over. So this is why I say it's very delicate. And with this, it just confirmed that the structural phase. Also look here. You see that I told you that it's not a typical shape. In order for me to insert this element inside this element, I need to cut these small lips, these flanges. And only after removing those flanges am I able to insert the element. But by cutting that, I make the element more vulnerable. Yeah. Okay. So if there are any questions, I'm here. I try to be on time. And if anyone has any comments, just chat here. And we don't have that much time, to be honest, but any feedback is welcome.
Yeah, but the platform on the video it was saying the acceleration was 0.6 G.
Yes.
But that's 50% more than we have in Rancha.
Yeah.
So it was over tested or stressed or something, that little house.
Yeah. You imagine all these experiments cost a lot and you want fireworks. So you want it to fail. It doesn't mean the structure is not okay. It means that it's fun to watch it fail. So don't worry about that.
Okay, that's philosophy.
You're totally right. This kind of structure have no problems with seismic forces. But it's also nice to see how it fails.
Hvala ti puno, Čiprijan, ovo je bilo kao i obično savršeno i nadasve inspirirajuće. Nadam se da su i ostali sudionici ovog našeg eventa da dijele moje mišljenje. Hvala još jedanput, Čiprijan, a sada najavljujem za sutrašnja predavanja, a to su Elena Popovska iz Tetova i Marko Veličković iz Beograda. Budite i s nama sutra, 3:00 počinjemo i za danas vam želim ugodan ostatak dana. Lijep pozdrav!